All right. Thank you, Paul, for the introduction. Hello, everyone, and thanks for having me here today. So I'm speaking on the topic uncertainties in high-risk MIP models in simulating rainfall over West Africa based on the choice of reference data. Now, initial parts of this work has already been published, and you can find access to it using this link. To begin with, I take you through the motivation for this work. At the beginning of my PhD, I had a goal of preparing a personal graded data for West Africa, which can be used for evaluating climate models and doing the downscaling and bias corrections of the climate models. In so doing, I spent my initial years contacting various meteorological agencies, trying to get these station data from them. Unfortunately, the feedback wasn't that positive. Some of them charging exorbitant prices for the data. I know it was just a means to deter us from getting the data. So in the long run, I had to drop and rather explore different climate data stores online to see if I can get access to this climate data. So just to mention a few of the data sources where I got the station data, I checked the climate data online from NOAA, the KNMI Climate Explorer, a site Pagoda eClimate, all to gather some station data. And my goal was to get data from 1990 to 2022. In all, I was able to gather 134 stations from 11 different countries across West Africa. And the countries that I selected were countries that at least had 6 stations available for the country. My initial target was for minimum temperature, maximum temperature, average temperature, and precipitation. Now, after gathering all these data sets from the station, the first thing I decided to look at is how the data looks like. The data gathered from the various meteorological stations online. Now, in all, we realized that over 60% of the data was missing for precipitation for each station. So it means that the precipitation data online was bad. Maximum temperature ranged between 17% to 90% of the missing values. Minimum temperature range between 19 to 85%, and the average temperature values range from 5% to 85% of the values missing. So these are just plots of various countries and stations showing the various data sets that were missing in terms of percentage. Looking at this type of data, it becomes difficult to evaluate models with such a data, even though we had the goal of taking them through the data process, quality control process, homogenization, and eventually filling the gaps. With such amount of data missing, even doing interpolations to fill the gaps was difficult. So in the long run, I had to drop that search. However, the work needs to be continued. So looking at the current state of the data, it means that getting in situ data or station data over West Africa to make a direct information about, especially for precipitation, is difficult. And West Africa is highly variable when it comes to precipitation, where precipitation changes at such a short distance. So if data sets is missing, it means that there is greater uncertainty when it comes to preparing any graded rainfall data set for the area. It becomes difficult for validating even satellite rainfall products. There is increased uncertainty in the precipitation trend since some of the years are missing, so you don't actually get the picture of that specific year. There is uncertainty also in extreme rainfall. And when it comes to model evaluation, it becomes difficult to draw any major conclusions when we rely on this station data. So as an alternate, I decided to rely on already created graded data sets for Africa. And these are a few of them that I worked with: the MS Web, the Era 5 Land, CHIPS, TAMSAT, and GPCC. Now you realize that all this reference data are a combination of different sources. For GPCC, it's mostly made up of the rain gauges from different station data, and the CHIPS and the TAMSAT sort of complement each other because they are both from infrared satellite observations. However, CHIPS inculcates some in-situ observations to their data sets, and we have the ERA 5 land, which is purely reanalysis. On the right-hand side are the tables that I worked with in terms of high-resolution models, the models I was working with. So straightforward, we go to our results. Now, 3 questions I plan to answer from this was to check whether the models are able to capture the annual cycle and variability, whether the models do well in reproducing the monsoon rainfall and its extremes, and if there is model bias, does the model bias cut across all the references we are dealing with, or the bias of every model happens to be a choice of the data set you are dealing with? So these were the questions I set to answer for this research. So in so doing, I divided West Africa into 2 sub-regions. We have the Guinea Coast and the Sahel. The Guinea Coast is a place where it's mostly wet due to its nearity through the equatorial belt. It is mostly having higher rainfall, and we have highlands that is mostly wet throughout the season. So for instance, we have the Cameroon highlands over here. We have areas closer to the Guinea Coast that is always having maximum temperature. And the Sahel is relatively dry most of the parts of the year. And we have the windward side, as I explained earlier, where we have the highlands. So first we check the annual pattern of the precipitation data set. We check for the Sahel, we check for the Guinea Coast and the entire West Africa. Now, what was seen among the models is that they are all able to capture the timing of the maximum precipitation. So for instance, over the Sahel, we have dryness from November through to March, the eventual rising of the rainfall until it gets to its maximum peak in August, which is well captured by all the models in these cases. And the reference data set mostly agrees also on this peak. Now, the only differences when it comes to the reference data is the amplitude or the intensity with which it captures. So in all the pictures throughout, one thing is seen clearly. The blue line over here represents the ERA 5 land. So we see that ERA 5 consistently gives low rainfall over the entire West Africa and its sub-regions. However, the other reference data sort of matches each other quite well. So ERA 5 is consistently giving a dry bias, and the INM model from the Russian Institute of Numerical Mathematics is always having a wet bias. So in most cases, we are seeing an overestimation over here in the sub-regions and the entire West Africa. So when it comes to the Guinea Coast also, we see that the amplitude disagrees most over the Guinea Coast. Then we looked at the interannual variability of these data sets over the years that we are dealing with. How is the data set varying from each other when it comes to its annual variability? The top column over here shows the reference data's variability, and down beneath shows how the models captured this variability. A general look at the picture shows that, for instance, over the Guinea Coast, most of the models give a completely dry period from 1983 to the early 1990s, where there was less precipitation. However, when you compare it to the reference data, there are few reference data sets like the ERA 5 and the MS Web that showed few non-dry seasons during this period. In order to quantify it, we looked at the correlation between each model and the reference data sets we are dealing with, whether there was a correlation when it comes to the interannual variability. A clear picture is seen over here that, for instance, over the Sahel, models were agreed much better with TAMSAT. The bolding text simply shows the statistical significant results where models had a statistical significance correlation with a reference data set. When you check the HIRAM model was able to get statistical significance for MSWeb, CHIPS, and TAMSAT over the Sahel and together with GPCC. However, when it comes to the Guinea coast, it was the ECMWF model that was able to get a better correlation with CHIPS and TAMSAT, which is way greater than the correlation observed over the Sahel, and the results were statistically significant. A similar picture was looked at the entire West Africa when we average both the Sahel and the Guinea coast. And a similar picture is also seen as most models tend to agree more with the TAMSAT variability, giving statistical results. However, the correlations move between low to medium, with the highest correlation being for the ensemble mean and the lowest statistical significance being for the Russian model. Then we looked at the monsoon season, how models are able to capture the spatial distribution of this monsoon season. So the monsoon season was defined as the season from June to September within a steady period. The picture was clear over here. The gradient is robust. That is, all models are able to reproduce the wet southern parts and the dry northern parts. So we see that mostly precipitation is concentrated over the southern part, which all the models were able to capture it clearly. One other thing that the high resolution models did well with was to be able to capture the highland, the Cameroon highland maximum, and the maximum around the coastal areas. Now, just as it was seen during the annual distribution, we see that INM model, the model from Russia, still shows a wet bias, showing more rainfall over this zone, and the rainfall even extends higher into the Sahel part as compared to the other references. Error 5 in this case still gives a dry bias when you compare the various references. Even though it's capturing the gradient all right, it's still showing low precipitation over the southern part. Then we look at the wet day frequency, how models are able to capture days that are wet. And generally, you realize that for GPCC generally gives a too many rain day season. However, GPCC happens to be the actual station graded data over here. So comparing it with the other references, you realize that GPCC is having many days compared to the others. What the models failed to do over here was also to give too many rainy days. For instance, drizzle models like the MPI, GFDL, and the rest show too many often rainy days, whilst the opposite was true for the BCC model and HIRAM. Now, Guinea Coast, as usual, captured the wet days, higher number of wet days. What generally these wet days point out is the issue with convection scheme triggering. So when it comes to the convective parameterization within the models, there is a challenge when it comes to West Africa. Furthermore, we looked at the heavy rainy days, that is the maximum 5-day precipitation over this season. So yes, we see that most models tend to overestimate this maximum 5-day precipitation when compared to that of the references. Error 5 is still giving a low bias over here. Comparing the intensity of the rainy days and the number of rainy days. Now, this is what we see. BCCC is giving few wet days, but even though it's giving few wet days, it's showing a very high intensity rainfall. So if it rains for only 3 days within the year, they are telling us that rainfall within that 3 days is such-huge. And the models with the drizzle, where it just takes any drizzle as a rainfall, show a week per day intensity. Among the most intense wet day was the HIRAM model. So you see over here that the HIRAM model extended over the entire West Africa, not showing any southern wets than the North Place. We look at a general picture of the distribution of this analysis that was made. So the first one over here represents the monsoon season. Then the other part represents the extreme precipitation index that was done. Generally, a clear picture is seen over the Guinea coast, where most models tend to have higher boxes. The boxes represents the interquartile range or the variability of the data set, the seasonal variability. So you see that seasonal variability increases mostly over the Guinea coast. Now we decided to represent this using, we decided to represent this using heat maps to show the biases within the data. So a clear picture over here, we see that since Era 5 reanalysis is always providing a dry bias, whenever models are compared to Era 5, there is an extreme overestimation, more than 80% of the data set for the sub-regions and the entire West Africa. The picture looks quite different over here when it's compared to the GPCC reference data. For the GPCC, you realize that models are not able to capture up to the amplitude of the GPCC, in most cases showing an underestimation. However, the underestimation over here looks quite average compared to the extremes that are recorded over the other regions, over the other references. What this one is also telling us is that with the ensemble means, we are always having smallest magnitude mean biases, showing that the ensemble mean tends to smooth the biases when used for any analysis.
Kwame, you've got 3 minutes.
Okay. We did a similar thing for the upper tails and the interquartile range. Generally, a similar picture is seen over here, Era 5 having had much upper tails. And for the interquartile range, the variability, a similar picture is seen as the biases over here. So Era 5 also models overestimating the interquartile range. Generally, working with Era 5 needs to be done with precaution from the picture created over here. And when working with the GPCC models, you realize that models are not actually able to capture well the station data set over West Africa. CHIPS and Thamsat consistently sort of complement each other. Now, both products are all from infrared, satellite derived. However, CHIPS inculcates some station data to balance it. What this synthesis is telling us is that with models like the BCC, the ECMWF, and the INM, whenever you are comparing for the wet day frequency, there are too many wet days compared to the reference data that we dealt with. When you are using the ensemble mean, the intensity tends to smooth out and the individual models tends to, and in other cases, it tends to inherit that of the biases from the individual models. Now, what does this evaluation? So the models, yes, establishes the pattern, maximum at the south, minimum over the Sahel. However, there is a trade-off when it comes to the frequency and intensity, where some models are able to capture too many rainy days. However, the intensity is few. Now, the uncertainty in the observations tend to look clear. For instance, when you compare Era 5 to GPCC, where most models overestimate the Era 5 reference, whilst they underestimate the GPCC reference. What this leaves us, so when you are evaluating over West Africa, it's best you do that over multiple reference data to get a clear picture. We advise the model developers to work on the convective triggering when it comes to the models. And the next stages will be to bias correct and work on downscaling approaches. Thank you very much.